Xanh rách men. Tập Hà Vương. Tên họ thầy là Tập á. Tên thầy là Tập. Electricity. Ôi đúng rồi, học từ trường với điện thật.
Okay, sorry. How are you? Fine? You're a little bit sleepy after lunch, it's normal. Me too. Okay. So, is everyone here? Yes? Okay, let's start. So, first of all, please let me introduce myself. So, my name is Tap Hazum. So, my first name is Tap, and my family name is Hazum. And so, as you see, I have a Vietnamese name, but I'm French, in fact. My two parents are Vietnamese, but I was born in France. Okay? And I am professor at the University Paris-Saclay, which is a university in the south suburb of Paris. Okay, so close to Paris, not in Paris. Okay, and as I said, I am going to teach you some fundamental physics 2 course, and more specifically, I will teach you fundamental knowledge about electricity and magnetism. Okay? I guess I have to tell you something about. Yes, I don't remember. Let me. Yes. Okay. Yes. I have to tell. Hello? Yes. So before starting, do you hear me like this? Like this? Okay. Okay. So first of all, I need to tell you that the final mark, you will have a mark. Okay. And this mark will be composed of 3 parts. Okay. So the first part is about your attendance in this course. Okay. But you are too many, so I won't count you each day. Okay. So the attendance will be for the tutorial. So you will have 7 sessions. Okay. You will have 7 sessions of tutorial work. Okay. And these 7 sessions tutorial work are mandatory. You have to go to these 7 sessions. Okay. If you miss more than 2 sessions without justification, okay, so if you miss 2 sessions, you won't be allowed to present the final exam. Okay? So during the tutorial work, there will be someone who counts you. Okay? And if you miss more than 2 sessions, you won't be able to present the final exam. Okay? So the first will contribute, the attendance will contribute to 10% of the final mark. You will have also a midterm exam, which will contribute to 30% of the final mark. Okay? So the final exam will be 30 minutes of multiple choice QCM question. And of course, you will have a final exam which will contribute to 60% of the final marks. And then you will have an exam of 60 minutes, and you have also a multiple choice QCM. Okay? Any question about this? Yes?
During your lecture, when I raise hand and contribute to cost, can I have 1 point? Have a bonus point?
Yes, I think that there is something on the screen. No, not during my course. You can have bonus point during the tutorial work. Okay? So, because it's too difficult for me to see who is asking and who is participating. Okay? Any other question?
The maximum bonus point is 2 points.
Yes, I think. Yes? Okay, so as you can guess, I won't present you the lecture using slides or PowerPoint files. Okay, I don't like this. And this is for one reason. So, what you will see is I am going to write here in this paper the course, the lecture. Okay? And this is for you because I strongly recommend you to take a pen and to take a sheet of paper and to write the course. Okay? Because there is study now which demonstrate that when the hand is writing something, then the brain is better. Okay? If you just look at the screen without noting, without writing something, you won't be able to understand everything. Okay? This is very, very important for me. You should have something to write, a pen and a paper, or, of course, you can use your computer, but it's less efficient to type on a computer. Okay? So later on you will have time to use your computer. So for the fundamental physics lecture, I strongly recommend you to take a pen and to draw. Or you will see I will make a lot of scheme, a lot of diagram, and then if you make yourself the diagram, if you reproduce the scheme, you will be better in physics. I'm sure of it. Okay? So, do you have any question before starting the lecture? No? Okay, yes. Just one last remark. I like to exchange with students. This is my pleasure of being professor, of being teacher. Okay? So, please feel free to raise your hand and to ask me any question. Okay? There are no stupid questions. Okay? So, I invite you to ask me any question that you want. But please, I don't like that you talk between yourself, among you, because I don't hear. Okay? So please keep quiet. Okay? But you are allowed to ask me any question, especially for the student on the back of the classroom. Okay? Okay, so now let's start by the first part of my lecture about electricity. Oh yes, that's me. My lecture is based on the textbook, which is Fundamental Physics by Halliday, Reswick, and I don't remember the third name. So maybe you have this textbook somewhere in your library, okay? And I'm telling you that because I am going to follow the numbering of the chapter of these books. Of this book, okay? So, in this textbook, the electricity part begins with the chapter 21, okay? So that's why I am going to number my chapters according to these textbooks. In that way, you will be able to read the books and to refer to these books, okay? Okay. Okay, chapter, so the first chapter about electricity is chapter 21. Okay? Okay, so just a few words of introduction. Electricity phenomenon. Okay, there are too much noise for me. Okay, so the electricity phenomenon was discovered maybe 1,000 years ago by the Greeks or by the Chinese. We don't really know, but how they so the Greeks have discovered some special stone, like amber. You know amber stone? Yes? Okay. And they have discovered that if we rub an amber stone with a cloth, okay, like this. So let's say okay, and then if we present the amber stone to straw, let's say straw, okay, so what they observe is that stone is able to attract the straw. Okay? So this is the first discovery of electricity phenomenon. Okay? So now we know that is due to excess charge. That means that when the can you read? I'm sorry. Sorry. Is it better like this? Sorry. Is it okay like this? Okay. So now we know that electricity is due to excess charge on the object. So that means that when you rub a stone with a cloth, you take charge or you give charge. It depends on the sign of the charge. Okay. So when you do that, we have some let's say some positive charge here. Okay. And the straw is known to be negatively charged. And then, that's why there is an attraction between the stone and the straw. Okay? But now, with modern physics, we know also that the elementary charge in nature are electrons. Electrons, you know that electrons are particles negatively charged, right? And protons. And you also know that protons are positively charged. Okay, this is nothing new about this. Okay? Okay, so this is my first slide. If you want me to keep the paper on the screen, tell me, okay? Because some, okay? Okay. Sorry? Okay. Can we go on? Can we continue?
Not yet.
No? Okay. Okay, this is a general introduction. Okay, so let's continue. Okay, so just I'm going to number a little bit my part. So now. So now in the nature we know that there are several types of electric material. We have insulate, we have conductor, okay. The characteristic of a conductor is that the charge, the elementary charge, mainly the electrons, are free to move in the material. Okay? The second type of main electric material is insulator. Okay? And on the contrary, in insulator, the charge, if they exist, cannot move, are fixed in the material. Okay? Okay, so these are the two main type of materials. But we have also. I won't enter into the details, but we have semiconductor. Okay, semiconductor. So are materials which can behave like a conductor or an insulator, depending on some conditions, mainly the temperature, for example. Okay, can behave like a conductor or an insulator, depending on conditions. And maybe the last type of electric material that you know is superconductor. Have you heard about this? In superconductors, the charge can move without resistance. We will see that about, okay? Charge. Okay. This is some general definition. We will see that after. Okay, so now let's enter into the details of the main law of electricity. And the main law of electricity is the Coulomb law. Okay, so I'm going to enter this. So 20. Okay, so let's consider one charge QA located at the point A in the space. Okay, and let's consider another charge QB located at the point B. Okay. So of course there is a line between A and B. And let's define the UAB. Maybe it's the phone. Okay, let's define UAB, which is a unit vector. Okay, a unit vector means it's a vector which length is 1. Okay, and UAB is a unit vector which is going from A to B. Okay. Okay. So the Coulomb law said that QA exerts on QB the electric force. Oh, sorry. Is it okay?
It's missing.
that out. QA exerts on QB the electric force. Oh, I'm sorry. Is it okay like this?
Chứ em thầy kia, em thầy kia nó không ổn đâu.
This is so in this formula, of course, the distance between A and B is noted R. R. Okay, so RAB is the distance between the 2 points AB. Okay? So in this formula, epsilon 0 is called the permittivity constant. Okay, and this constant equal 8.85 times 10 to the power 12 Coulomb. Yes, I'm going to talk about this. Coulomb C divided by Newton and meter squared. So Coulomb is the unit of charge of QA and QB. Sorry. I don't know how to, maybe like this. Is it better?
Yes. Nó better, em cũng không biết kia là chữ M.
Okay. So just also, so if you, so pi is the number. So we also note this 1/4p epsilon 0, and if you calculate this, it is equal to 8.99 10 to the power 9. So now it's Newton meter square times Coulomb. Okay? So this is the basic fundamental law of electrostatic between two charges. Okay? So two charges, if you consider two charges, then you will have a force between them.
Em không biết đây là chữ gì.
Of course, so just a remark, if the product QA times QB is positive, that means that the two charges are the same sign, then the force is repulsive, okay, because the QA will be repulsed by the QB will be in the same direction as UAB, and so there will be a repulsion. But if the product QA times QB is negative, meaning that the two charges are of the opposite sign, then you can see that the force will be in the opposite sign direction of UAB, so in that direction, and then the force is attractive. Okay? So I'm going to write this. Remark. If QA times QB is positive, then FAB is repulsive, and if QA times QB is negative, then FAB is attractive. Okay?
Adjective cái gì kia?
Another remark.
Diffusive.
We know, so let's say it's part 2, 1, sorry, 3. We now know that in the nature, the elementary charge is the charge of an electron. Okay? And so all the charge in the nature is equal to an integer time E. E is and the elementary charge is 1.602 times 10 to the power minus 19 coulomb. Okay? Sorry?
He asked this
Quantize, it's a Z. Quantize. That means it's a quantum of something. Yes?
Can you repeat the formula?
The required, please.
Can you repeat the first formula?
this one.
This one?
Yes.
Q. Okay, quiet, please. Please. Okay, so this equation means that any charge in the nature is a number, an integer, multiplied by the elementary charge E. Okay? Of course, plus or minus. Okay? This means quantized. Okay? Did I answer your question?
Yes.
Welcome. Okay. Can you other question? No? Okay. So the next remark is electric force are additive. That means that if you have one charge Q1, a second charge Q2, another charge Q3. Then, if you are considering another charge Q, then the charge acting on Q is the sum of all the electric force created by the individual charge. So, okay, so for example, you have F1 here, let's say F2 here, and maybe F3 here. Okay, so FQ but the thing which is important is this sum is a sum of vectors. Okay? It's okay for everyone?
Yes.
Yes? Great. Okay, so now let's move to the next chapter. Okay, the first chapter is the Coulomb law. This is the fundamental law of electrostatics. Okay, so now let me talk about a very important notion, which is the electric field now. Okay, so this is the definition. So what is the electric field? The electric field is by definition related to the electric force. Okay, so I'm going to write the definition and I will write some equation. Okay, so any charged object create around it an electric field which is often noted big E, okay, so that if we place a charge let's say Q, this charge is called a test charge. If we place a charge Q called a test charge around, let's say around this object, let's say, if we place around this object, charge Q, how can you say, close to this object, let's say, then then Q will be submit to the force F equals Q times E. Okay? I repeat. So any charged object create around this object in space, okay, an electric field, so if we put somewhere a charge, a test charge, Q, then this charge will submit a force equal to Q times E. Okay? So it is important to note that E is independent from Q. Okay? That means that the test charge Q, the field, the electric field E, exists without the charge Q. Okay? It is only created by the charge object. Okay? So, sorry?
Take the paper up a little bit. It's the tip. Yeah, okay.
That's okay, there is nothing else. So E is an abstract quantity which is independent from the test charge Q, okay? Any question? Yes? No? Great. Okay, so as I said before, electric field is something abstract. We cannot see them. Okay? It exists around us, around charged object, but we cannot see them. But it is important to clarify the thing that we can draw them. Okay? So let's say yes we can. Let's say represent electric field with what we call electric field line. Okay, so what are electric field lines? So of course, lines that are lines which, first condition, which are tangent to the electric field at all points of the space. the lines also are oriented from positive charge toward negative charge. Okay. And the third characteristic of electric field line is that the density of line, of course, is proportional to the magnitude of. Okay, so let's take some example. Okay, so let's consider one charge, Q. Okay, for one charge, we know, because we know the force, okay? So, let's say, are we going here? Let me, the electric field created by one charge, one particle charge. Okay, is because of this. See, you remember this force? Okay, so if we can isolate this force, is so this is the electric field created by one charge particle Q at the position R, okay, and U is the radial unit vector. Okay, so we know that electric field around a charge particle Q is like this. Okay, Q here. Okay, are you agree with that? Yes? So now the orientation of the electric field is depending on the sign of the charge. Okay? If Q is positive, then, as I said before, the electric field are going from the positive charge to the negative charge in that direction. Okay? If Q is negative, of course, the electric field will be oriented in the opposite direction, in that direction. Okay? And now, the last example, if for example, we have a big Q which is higher, larger than small q, then as I said, the density of lines should be proportional to the magnitude of E. So what we will see is this. I mean, what we will see, it's what we represent. Okay, so here in this last example, you can see that the density of lines, there are much more lines than in the first example. You see? Okay. And sorry, in this direction, of course, the vector u is like this. They are almost and R in this equation, R is the distance from the charge. Okay, so it's, for example, here, R is this R here. Okay. Is it okay for everybody? Yes? Okay, let's consider another example. So imagine a sheet of paper, a vertical sheet of paper, and imagine that the sheet of paper is there is a lot of charge here, for example. In this example, we will see that the electric field is perpendicular to the plane of paper and is going like this, and is going in that direction because the sheet is positively charged, and in that direction also. Okay, so this is. I can draw a lot. If you have two charge, for example, two positive large charge, okay, and then the electric field is represented like this. so it is just to remind you this. It's just because I forgot this. So here, this is important. So in this equation, again, U is a radial unit vector. R is the distance between the charge and the point M where the electric field is calculated. And Q is the charge which creates the electric field. Okay? Okay, so now let's complicate a little bit the problem. What is the electric field created by a dipole? So, what is a dipole? A dipole is an ensemble. Let's make definition. Of two opposite charge so plus Q and minus Q separated by a distance d. Okay, so we have minus Q plus Q, and here the distance d. Okay. This is a dipole. Two charge minus and plus. Okay. And we define the dipole moment P equal QD. Okay, so time a vector from, let's say, a unit vector going from minus to plus. Okay, that's why I'm going to draw it here. So let's say this is U minus plus. That means that the unit vector is going from the minus charge to the positive charge. Okay? And so the vector P is equal as QD and is like this. Okay, so now we are not going to solve all the problem, just I'm going to restrict a little bit the question. Okay, so the question is, what is the electric field created by a dipole at a point M of its axis. Okay, so in other words, we have the dipole axis here, minus Q, let's say O, plus Q, okay, D, and we want to calculate we want to determine the electric field created by the dipole at the point M, okay? And the point M is here. So we can use here the axis U here. So, as I said before, the electric forces are additive, so the electric field also are additive. Okay, so the electric field at the point M is equal to the electric field created by minus Q plus the electric field here created by the positive charge plus Q. Okay? Are you agree with that? Yes? And so we can now write that this is equal to 1 over 4p epsilon 0, the charge minus Q, divided by the distance between this and this. So let's say that, so O again is the center of the dipole, okay, the charge are here. And so, and M is distant from a distance R from the origin, the center of the dipole, okay? And so the distance between the charge minus Q and the point M is equal to R plus D over 2, right? Yes? No, time U. So plus 1 over 4p epsilon 0 time plus Q over R minus D over 2 U. Ah, thank you very much. I forgot the square, no? No? There is a square, no? Okay, so we can see that this is equal to 1 over 4p epsilon 0 times a Q, sorry, Q. So minus 1 plus okay, and if I calculate this, this is equal to a big ratio of so now if we okay, so I have someone told me that the Vietnamese students are very good in math. Is that true?
No.
Come on, it's true. So you have to watch me, okay? Because sometimes I make mistakes. Okay? So we can, and then we have this. So tell me if I am wrong if I say that this is also 2 minus this is
Thế là em hỏi chủ trương tại ngư chủ trương
and here we have oh yes, we have
cái này phốt này cũng gần gần giống đấy, rồi gần giống e rồi
Is it correct? Yes, no? Okay, so let's continue. So okay, this is the general, but usually what is important is to consider the electric field far from the dipole. Okay, so if we consider this. Okay, if the distance r here is much more larger than the distance d, okay. Okay, so we are going to write this. E of m equal. See, I'm going to take out the r here. So, yes, oh yes, okay. So, see here, if r is much larger than d, so this term is yes? No? You have a question? Okay. So this term is negligible. So we have R2 times squares, meaning R4. But here we have an R. So at the end we have yes, 2. Two QD over R3. Okay? You can see. And QD is equal to P, so this is the electric field created by a dipole. Okay? And I'm going to show you the electric line. and the electric line is resembling like this. So this is in between the charge. And so here is the electric line. Here are the electric lines created by a dipole around it in the space. Okay, and here if you are here M, the field EM is like this. Okay, but if you are here, for example N at the point N, then the field is like this. But if you are, okay, this is the electric field created by a dipole. Okay, please listen to me. I'm not asking you to learn by heart the formula of the electric field. Okay, this formula is not necessary to learn it by heart. Okay, but you have to know how to retrieve this equation by doing all this calculation. Okay? Okay, so now let's complicate a little bit the problem. So it's 22 times 4. Okay. So now what the question is, what is the electric field created by a continuous line of charge? So let's consider a line, whatever, okay, and the line is bearing a lot of charge. Okay. Let's say Q. So of course we cannot now, because the continuous, we cannot separate the line, the charge. Okay, so the line is characterized by lambda. We call it the linear density, charge density. Okay, so lambda is the number of charge by length of the line. Okay, so linear charge density. So the question is, considering this line, what is, for example here, at the point M, what is the field, electric field, created here by this line? Okay? Okay, so again, I don't want you to learn the result. Okay? I just want you to know the method to find the result. Okay? So, here we have a continuous line of charge. So, what we are going to consider is to consider a small length. So, it's a very small length, a very small part of the line. Okay? And this small part of the line is bearing the charge dq. It's a small dq, okay? And if you dq is equal to the density of charge time the length dl. Do you understand this? Okay? We have decomposed the line on with small dl. Do you understand this idea? Yes? It's a very common way of thinking in physics. Okay? When you have a lot of a macroscopic object and you want to know the effect of this object on something, then you decompose this object into small parts, microscopic parts. Okay? And then, because this macroscopic part, you can create this dl will create something like here a small de. Okay, so the method is the one. So decompose the line into microscopic small parts dl. Okay. Then each dl has the charge dq equal lambda dl. Each dl creates the field because it's a small charge, so it created a small field which is called dE, and then make the integration, make the sum of all dE. Okay, so that means that when you add a lot of small things, okay, in physics, it is equivalent in math of making the integration. You know this sign? Yes? This is the integral. Okay? It's like a sum, but it's not a discretized sum. It's a continuous sum. Okay? Okay, so let's apply it to a concrete example. So, of course, for example, here, yes, I can. So now the DE, here is the DE. The DE is the electric field created by a very, very small things which can be assumed as a point. Okay? So this is equal to 1/2. Okay? So now we can apply the Coulomb law. the small dm is 1 over 4p epsilon 0 times the charge is equal to lambda dl divided by the distance here, okay, times u, and then you have to make the sum. So at the end, the but this function here is complicated, okay? So we need to consider some special case. So okay, let's see. This is difficult to calculate in the general case. Okay. So how? So an important trick to do the calculation is to consider symmetry. It's very important to consider the symmetry of the problem. Okay? So let's do together a calculation. Okay? An example. You need to, it's okay? Can I continue? Yes? Okay, so let's do an example. Let's consider a circular line. Okay? And so here is a circular line, okay? And we are going to restrict the problem. And we want to know, so of course, this line has a lot of charge here, let's say Q, okay? And so we want to know the electric field at the point M. Okay? So we are going to, as I said before, we are going to consider, for example, the small here, dl, okay, the small dl is creating the small here, de at point A, okay? But if I consider the symmetric one, dl prime here, okay, this small dl prime, we also can create the field de prime at the point M. You agree? Yes? And by symmetry, if you make the sum of the two, okay, so by symmetry, dm plus de prime at m is axial. That means that it is on this axe u. Okay? So this is why it is important. This simplify a lot the calculation. You will see. So okay. So now let's enter the detail. So let's introduce the z. Okay, z is the distance OM. Okay. Let's say big Z is the distance between each point here, between DL and M. Okay? And of course, R is the radius of the line. Okay. So, now the electric field created by the circular line at the point M is, as I said, the sum, but I can also write this on half. Instead of making the sum of all the dl around all the circular line, okay, so I can make the sum on half of the line. Do you understand why? Because here in this integral I have considered this dl and this dl prime. You understand? Is it clear? And so we will obtain something, we don't know what here, but time u, because the sum of these two vectors, we know that the sum of the two vectors is aligned with the vector u, the unit vector u. Okay? So what is it inside here? Okay, so now to determine what is inside, we are going to apply the Coulomb law. Okay, so the field created by dl is equal to the first one over z squared, okay, let's say so u, how can I do that? Let's say b. Unit vector, let's say b, let's say b. B is the unit vector here. And this point is, okay, plus 1 over 4 b times lambda dl prime v squared times but dl and d prime, sorry, yeah. Okay? So, this sum is equal lambda dl over 4p extend to b squared b plus b prime. Okay? B plus b prime. And now v and b prime are unit vectors. Okay, so if I introduce the angle here, theta, here. Can you see? Theta? Do you follow me?
Yes.
Yes? Okay. So if I introduce the angle theta, we have v plus b prime equal 2 cos theta times u. Are you agree with that? Because v and b prime are unit vector. Okay, yes? So, now, so we have d e of n plus d e prime at m equal lambda here over 4b epsilon 0 b2 times 2 cos theta times u. Okay? So, see, as I say, this sum of the two vectors is equal to something times u. Okay, so now we want to add this. Okay, so first I would like to introduce small z. Okay, so cos theta is equal to small z over big Z. Okay, and we have z, the distance z is equal to, now I want to introduce the radius. Are you okay with that? Yes? Okay, so at the equal Are you agree with that? Yes. Please quiet.
This big R, this small R.
No, this is small z. This is small z. Z is the distance between O and M. Here.
Small g. Vừa quá. Cái gì?
And I forgot you. It's okay? Yes? Can we continue?
Can we have a short break?
Sorry?
Can we have a short break?
A short break? Not yet. I want to finish the calculation, okay? It's not, it will be maybe the only calculation that we make together, okay? But the point is I want you to be able to do something, okay? Okay, so, it's not finished, okay? So at the end,
Cái Z này, cái Z là cái Z hình như không.
okay, but in this integral, everything is constant, okay? There is only one variable here, which is dl, okay? So at the end, only so at the end you have 2 v lambda over 4 e epsilon 0 r2 plus v2 . Okay? So at the end you have only to add this dl. You understand what I mean? So if you add here the dl on half of the circular line, so what would you obtain? What is this here? According to you. What is the sum of the small dl over half of the circular line? Someone. Come on. Okay, so my question is, what is the length of a cycle? 2 pi r, right? So what is the length of half of the cycle? Pi r, exactly. Okay, so you can see that at the end, have 2 pi r v lambda over 4 pi epsilon 0. Okay. This is not, the result is not important. Okay. Is it okay for everyone? Any question? Because now we are going to complexify a little bit more. Yes, are you ready? Not yet, okay. So okay, my remark is
có DG bằng phi R. Đúng không?
do not learn the result, but the method. Okay. It's okay? Can we go on? Sorry?
Let's continue.
Let's continue? It's okay? Okay. Okay, for the first course, I'm sorry because I have to go fast, so please, 1 hour, okay? It's, I have to finish at 3. Okay, so let's continue with the chapter 23. So, as you can, I don't know if I need to do this. Okay. Okay, so I'm going to complexify a little bit with a last example. Okay. But again, the idea is to show you the method. Okay, so 22.5. So what is the electric field created by a charged disk now? Oh. Okay, so now we, instead of here, instead of having a line of charge, we have a disk, so it's a surface with plenty of charge here. You see? And I'm going to ask you, what is the electric field at the point M? Okay, so again, we have the axis U here. Okay, so I won't enter into the detail, but I will show you how to do it. You have an idea of how to calculate, the electric field at the point M. Okay, so I forgot to mention that the disk is characterized by sigma, which is the surface charge density. Okay? So this is the number of charge divided by 1 unit of surface. So according to you, how are we going to calculate E of M? Okay, the idea is to decompose the disk into many rings. Okay, so let's say, so we are going to, So we are going to decompose this surface into very small surface, like ring like this. Okay? So this is a ring, a charged ring of radius R, okay? And the thickness is a small dr, okay? So R is this here. And this is the thickness dr, okay? And this ring has a charge okay, because the thickness of the charge is very small. So the charge of this ring here is equal to sigma, the density of charge, times the surface of the ring. So what is the surface of the ring? Is 2 pi r times dr. Okay? So this is important. Okay, so I repeat. We are going to decompose the disk into small rings here. Each ring has a radius r and the thickness dr. Dr meaning that it's a small thickness, very, very small, okay? And so this ring has a surface of 2pr times dr. Are you agree with that? So the charge of this ring is dq equals sigma times 2pr dr. It's okay? Okay. So, and now we know that the ring, the charged ring, creates the electric field, let's say dE at the point M, okay, M is here. And we know previously that this field equal here something like this. Okay? But instead of lambda, we have something, let's say something times u. U being the vector. Okay? We don't care about what it is, but we know that. Okay? You understand what I mean? Yes? The thing that in the bracket here is something like this. Okay? And then the total, just have to say that the total electric field at M is the sum of all the rings all the contribution of the rings, okay, of the DEM. But because all the DEM are proportional, it's easy to calculate this thing, okay? And because the R is going to 0 to big R, big R it's the radius of the ring. Okay? And then you can replace this by something. And this calculation is easy. It's a math. Okay? And I'm going to give you the result. So at the end, it's not important. Okay. Again, it's not important. Okay, I'm just giving you the result. Okay? So again, it's not important the result. It's important to understand the method. Okay? Each time when we want to calculate the electric field generated by a complex object, we need to separate it, to decompose this object into small elementary charge. Okay? Do you have any question? Okay, so let me start the new chapter, which is chapter 23. Yes?
Can you take back the last? Yeah. Okay.
Of course, Z is the distance between O and M. Z is the distance between O and M. Please, sit down. It's not finished. Okay. A little bit, some effort. Okay. Do you have any question about this, about the electric field? Okay? Okay, so now we are going to simplify a little bit. So, as I said to you, we are able to calculate the electric field by decomposing a complex object into small components. But the calculation is long, it's time consuming. Okay, it's not difficult, but it's long. Okay, so hopefully for us there is another way to calculate the electric field more rapidly. Okay, by using a Gauss law, which is the object of the chapter 23. So, chapter 23, the Gauss from the Gauss law. And I will show you how to use this law to calculate more easily the electric field. Quiet, please. Quiet, please. Any question? Shh. You have any question? Okay. So, in order to present you the Gauss law, I need to introduce you the notion of electric flux. Okay, so imagine a surface. Okay, which is placed in an electric field. Okay, so at the point M of the object, there is an electric field. We defined for this surface, so this is a surface, small area. Okay, small surface. So for this small surface, we define the vector dA. So this is, what is dA? dA is a vector perpendicular to the small surface, perpendicular to the small surface, and which magnitude is equal to the surface, to the area. Okay, so we have a small surface like a coin, and we have a vector dE perpendicular to the surface, and the length, the magnitude of this vector is equal to the area. Okay, here. Okay. This is it. So now, if we put this small surface in an electric field, okay, we define the flux definition. The flux of E through the small surface, so dA, is, by definition, we note it phi, it's the dot product E times dA. Okay? Sorry, it's a small flux, so it's a dphi. Okay. Okay, so this flux, what is the physical meaning of this flux? The flux represents dphi, represents the amount of electric field which, let's say, pierce the surface dA. Okay? Oops, what happened? Okay, okay. So of course, this is a small. Quiet, please, quiet. And now, if we, let's say, consider a big surface. So now, and so this is a big surface. Of course, for a big surface, the flux is the sum of all the flux. Okay, so it is the sum of E scalaire dA, where dA, okay, dA are small area like this. Okay? Again, you can see that we decompose a big area. So this is A. Okay? We decompose, etc. Okay? So this is dA. Okay? Okay, just unit. What is the unit? Of course, the unit. According to the definition, the unit of phi is Newton meter square times 2. Okay, so let's do some few remarks. If the surface A, let's say for example like this is A. If the surface A is parallel, okay, then the dot product is equal to 0, right? So here, for example, okay, there are no electric flux if the surface A is parallel to the electric field. Okay. Okay. Let's go here, because here, for example, so if the surface is parallel, then because dA is perpendicular to the surface, perpendicular to the A. Sorry. Yes, there is no here. So, because E is perpendicular to the surface, then the product E dot dA equals 0. Okay, so okay, but this is a remark. Okay, so now let's another definition. If for a closed surface, okay, we phi equal for a closed surface, we add to the integral this sign, this small ring here, meaning that it's a closed surface, and we call the net flux. Okay, this is the net flux through A. Okay, but in the case, for this is a closed surface, for example. In the closed surface, we need to specify that the vector dA is out where? Okay? If the surface always outward. Okay? So okay. So I repeat, in the case of a closed surface, the vector dA is always outward, meaning that it's going to the surface to the outside. Okay? From the surface to the outside. Not, very importantly, not toward the inside. Okay? Always toward the outside. And in that case, we call the sum over all the closed surface the net flux. Oh, it's only a definition, okay? Okay, so now let's do some examples. Oh, yes. So remark. If the flux, the net flux of an electric field toward a closed surface is negative, okay, that means that E, the electric field, is piercing inward. Okay? And of course, because the net flux can be positive or negative, so if the net flux is positive, that means that the electric field is piercing outward. Okay? Okay, so let's consider an example to be clear. Okay, so let's consider it's not exactly a cylinder, but something like this. It's kind of a tube, but with different sections. Okay? Ah, no. No, this will be complicated. Okay, sorry. So it's a cylinder. So the cylinder is the length is L, okay, and the radius is R. And this cylinder is placed in somewhere where there is an electric field E. Okay? So the flux, of course the cylinder is a closed surface. Okay? So the net flux equal. So this we call this surface, this is S1, this is S2, and this is this L, like lateral. So the net flux is equal to the flux of the electric field through S1 plus the flux through SL plus the flux through S2. Okay? Now in this equation, the flux through the lateral surface. What is it? What is the value of the electric flux through the lateral surface here? Zero, yes, good, because E is parallel to the lateral surface. Okay? Okay, so now if we consider the flux through S1, we need to introduce here the vector U, let's say, yes, A1 here, and for the second, okay, so the flux through S1. So see, the important point here is that the vector A1 is opposite to the vector E. Do you see that? Yes, A1 is opposite to E. So the dot product is negative, so this is equal to S1E. But with a minus sign. Okay? And the flux of the electric field through S2 equal plus S2E. Okay? So at the end, the net flux is equal to S2 minus S1E. And because it's a cylinder, okay, so it's equal to 0. Okay? So is it understood what is the flux of the electric field? Yes? Okay. So now I can present you the Gauss law. So the Gauss law relates the net flux of an electric field to, of course, through a closed surface to the net charge, so the net flux to the net charge inside the surface. Okay, so let's consider the surface, the closed surface. Okay. Let's consider this is a closed object, and let's say the charge within inside. Whatever. So at the end, okay. So the Gauss law says that epsilon 0 times the net flux, okay, is equal to the charge inside the surface. Okay, so in other words, Q inside equal epsilon 0 times the integral of E times Okay, so here Q inside is the sum of all the charge inside. Okay? Q inside equal all the sum, okay, inside. Are you agree? Okay? It's okay? So this is the Gauss law. Okay, so just one remark. Okay, so another. Okay, so now let's apply this Gauss law to some specific case in order to learn what does it mean. Okay, so just first a remark. The Gauss law includes the Coulomb law. Okay, so let's apply what I'm going to do. I'm going to show you that. Okay, so let's consider a charge Q. Okay? So, as I said in my introduction of this chapter, the Gauss law is very useful. You will see it is very useful to rapidly calculate the electric field created by something charged somewhere in the space. And I'm going now to show you how. Okay? So let's consider a particle Q. Okay? And we want to calculate the field at point M. Okay? Okay? So, how can we do it? How can we know the answer already? Okay? So, I would like to show you that by using the Gauss law, it's very easy. So, what we are going to do is to consider okay, so this is the spherical surface. Okay, this is the spherical surface, center here and going through air. Okay? You understand what is it? Okay, of course, the radius here is r. The distance between the 2 points is r. Okay, so the spherical surface has a radius r. Okay? Okay, so now let's apply. So we know, of course, we know that the electrostatic field, the electric field is radial. Okay, so we know that because we are okay, so we know that the electrostatic field is radial. Okay, and if we consider here the small the dA, the small dA here, this dA is also radial. And you agree with that? Because on the spherical surface here, on the spherical surface, all the small surface are perpendicular to the surface. Okay? Or radial. So, according to the net charge inside, Q inside. So of course Q inside is equal to Q. Okay. And according to the Gauss law, this is equal to epsilon 0, the flux, the net flux. Okay. So Q equal epsilon 0, the sum of the dot product dA. Okay? But we know that for all the points on the surface, okay, we can see that E and dA are in the same direction. So now we can delete the vector. It's just the magnitude of E times the magnitude of S. Is that correct? Okay? But we know that the magnitude of E for all the position, for all the points on the surface is the same. Okay? So Q equal E times the integral, epsilon 0, times the integral of the dA. This is, what is the sum of all the dA? So this is equal to the surface of the spherical surface. So what is the surface of a sphere? Okay, what is the surface of a sphere? Louder, please. No? Okay, there is 1 point bonus for someone, for the student who can answer. No? Raise the hand. What is the surface of the sphere? Raise your hand. Yes? Louder?
Four by P, 4 by R, power 2.
Yes! Very good. Okay, so here at the end you can see that Q equal 4 pi epsilon 0 R to E, and then of course you can see that E equal Q so over 4 E epsilon 0. And this is the Coulomb law, no? Do you recognize the formula? Okay, so this was a simple example. Okay, so let's do a more complicated example. So now we have here, this is a spherical surface, okay, and and there is a density of negatively charged here. Okay, so this is a spherical surface, okay, or a shell, you can say a shell, with charge with Q equal minus 16 electrons, and the radius is 10 centimeters. Okay, and now at the center of this sphere, I put another charge, which is Q. Okay, Q is equal to whatever, we don't care. Okay? Okay, so my question is, can you calculate the electric field at the point P1 here, and can you calculate the electric field at the point P2? Okay? So the question is, what is the electric field at the point P1, and what is electric field at the point P2? Okay? So P1 is inside the spherical surface, and P2 is outside the spherical surface. Okay? So, of course, this could be made by adding and calculating all different parameters. But I'm going to show you that using the Gauss law, it's very easy to calculate this. So, again, again, don't learn the result, okay? Learn the method. So, for P1, we are going to consider a sphere going through P1. Okay, so this is R1. Okay. And of course, for P2, we are going to do the same thing. We are going to consider a sphere going through P2. Okay? So let's consider this S2 and this S1. Okay? So S1 is the spherical surface going through P1, and S2 is the spherical surface going through P2. Do you follow me? Yes? Okay. So now let's apply the Gauss law first through S1. Okay? So through S1, the charge inside, it is important to, okay, the charge inside S1 is only Q, small q, no? Because all the other charges are outside this, okay, so Q equals epsilon 0 V through S1. Okay? And what is the flux? So, of course, again, the flux of the electric field through the surface S1 is equal to E of P1 times the surface 4P R1 squared. Yes? So, from this, it is easy to calculate that the electric field at point P1 is equal to Q over 4P epsilon 0 R1 squared. Again, we retrieve the Coulomb law. But what is important here to note that the electric field at the point P1 seems to not depend on the charge outside. Yes? Okay. So now if we do the same thing for the charge S2, the surface S2, through S2. Okay? So now inside the surface S2, the total charge is big Q plus small q, right? And is equal to epsilon 0, the flux of the electric field through S2. Okay, and this is equal to the electric field at point P2 times the surface 4PR2 squared. Okay, so wait. Yes, okay. So at the end, the electric field at point P2 is equal to big Q plus small q for okay? So you can see that using the Gauss law, it's it's more easy, it's easier to calculate an electric field like this, instead of making all the integration of the small. Okay? Okay, let's do a last example, okay, and I will finish this. I mean, last example for today. Okay, so this is okay, so what is it? Okay, that's 23 point. Okay, so let's determine the electric field created by an infinite line of charge. Do you remember this? Okay? We already have this question. Okay? So I know we didn't do that, but we could do that. Okay, so we have an infinite line of charge, and this line is bearing a lot of charge. Okay. Okay, and the question is, if we consider a point M here, for example, so what is the electric field at the point M? Okay, and of course, M is characterized by the distance R to the line. Okay, and the density of charge on the line, the linear density, is lambda. Okay, you remember lambda is the linear charge density. Okay, so how are you going to solve the problem? Again, we are going to use the Gauss law. Okay? How? We are going to consider a cylinder which pass through this point M. Okay? So here is a cylinder. Here. Okay, so this is a cylinder. So the length is, let's say, L, and the radius, of course, is R. Okay? Okay, so we also know that at the point M, if we look at, okay, if we look at here, for example, okay, we will obtain this. Let's say O here. O. This is M. And we know that the electric field are radial like this. Okay? Okay, so that means that the electric field, so let's say S1 here and S2 here. Okay. So if we apply the Gauss law through this cylinder surface, we have the net charge inside. What is the net charge inside this cylinder? The net charge Q inside is equal to lambda times L, right? The charge density times the length inside, okay? And the flux through this cylinder equal, so what, through S1, so again, through S1 plus through the lateral surface and so we now with, of course, through the flux of the electric field through S1 and S2 is equal to 0 because the electric field, the vector electric field, is parallel to these two vectors, right? And the flux of the electric field through the lateral surface is now equal to the electric field times the lateral surface. So what is the lateral surface? It's 2πr times L. Okay? So at the end, we have lambda L equal epsilon 0 times 2πr L times E at the position M. And so the electric field, of course, this result does not depend on the length L, of course. Okay? You can see that it is equal to lambda over 2p epsilon 0 r. And that's it. Okay? So there is, you can see in half a page we can calculate the electric field created by something which is a little bit complicated, but without complicated calculations. You understand? Is it okay?
Yes.
Okay, thank you for your attention. Okay, so see you